This is lecture video 35, and in this lecture, we will cover the relation between the area under the curve and the definite integral. So recall that before we covered the area under the curve is given by the definite integral only if the function is positive there. So let's say you have a function like this, and you want to compute the area under the curve, okay, over the interval AB, then since we draw a positive function here, this is your x-axis, this is your y-axis, so our function is always positive, then this definite integral gives you exactly the area under the curve, okay? Under the curve, let's name it as A, for example. So this time definite integral is the same as the area under the curve. But this is not the case when your function gets some negative values, okay? So let's draw our function like this. Now, let's say it is always negative over the interval AB. And in this case, if you compute this definite integral, what you will find is not the area between your function and the x-axis, but the minus of it, okay? So this time, if you call this area as A again, okay, A, then the result will be minus A, okay? So, and the crucial thing here is that your function being negative all the time. That's why its integral will be negative. If your function is negative, its integral is negative, but there is still a relation between this negative integral and the area between your function and the x-axis. It is minus A, okay? So the area is always something positive, you know. That's why you need to put this extra minus sign to represent your negative integral as the area. Or your function may take sometimes positive, sometimes negative values like this, for example. Let's put here a function like this. And let's say we are interested in this interval from A to B. And let's name this point as C, this point as D. Now, if you integrate this curve y equals f of x, if you integrate f of x from A to B, then this result is not, again, the area under your curve. Not exactly the same as the area under the curve, because as you can see, your function also gets negative values. Over the interval CD, the integration is negative. So that's why, okay, if we shade these areas like this, and let's name this part as A1, this part as A2, and this part as A3, the result of the definite integral goes like, okay, integral over A to C is A1 because the integral contributes positively. It is the same as the area, which is a positive quantity, but over CD, the integral contributes negatively. That's why you need to put an extra minus sign to the area A2, and then here, integral contributes positively. That's why it is the same as A3. You see, we have this important minus sign here. So now let's try to relate the result of the integral and the total area under your curve. Okay, this total area is obviously what? It is obviously the sum of all these A1, A2, A3, okay? And as you can see, the definite integral is different because of this minus sign. Definite integral is different than the total area. And if you want to express the total area in terms of definite integrals, you need to go like this. Okay, from A to C, you can integrate your function to obtain A1. And then from C to D, you will find integral. But over here, you know, from C to D, if you integrate your function, you will find minus value of the exact area. That's why, since the integral contributes negatively over CD, you need to take the absolute sign of it, because the integral is negative. For the area, you need the positive version of it. So you want to search for this. That's why A2 is, if you take the absolute sign, it will be exactly A2. Okay, so let's just put our absolute sign and then plus from D to B. There is no problem because your function is positive again there. Only for the part over C to D, you need to take the absolute sign where the integral is negative, but you need the positive area or A2. So, okay, A2 is the absolute sign of that negative integral there. Okay, so the relation between the definite integral and area under your curve goes like this. If your curve is always positive, no problem. Definite integral is the same as area, but if there are some intervals where your curve becomes negative, then the area, which is a positive quantity, is the minus version of the definite integral, or in other words, if your function is negative, the integral will contribute negatively. Okay, so let's look at this integral. We want to find the shaded area by using definite integrals. So we can start like this, shaded area. Let's call it as A. It is, in fact, okay, let's try to use the definite integral from pi over 6 to 5 pi over 6. The integral of this function, sine x dx. Okay, what is this definite integral? It will give me the whole total area from, everywhere. Over this interval, the area under this curve is this whole shaded area, but I just need this part of it. That's why from this total area, I need to subtract the area of this rectangle. So how do you compute the area of the rectangle? Height times the base, right? What is the height of it? It can be evaluated by this curve. So pi over 6 is the x point. So this point is sine pi over 6. So this is the height. Sine pi over 6 times the base, okay? 5 pi over 6 minus pi over 6. As we said, this is the height of the rectangle, and this is the base of the rectangle. And if you subtract this value from this definite integral, you will find the required shaded area. Okay, the result is, what is the integral of sine x? So you need to consider a function whose derivative is sine x. But I think what is the function whose derivative is sine x? So in other words, we are trying to find the antiderivative of sine x function. So it is minus cosine x from this value to this value minus this thing. Sine pi over 6 times 4 pi over 6. Okay, I will leave it like this for now. Okay, let's move on. Another area example. So we want to find this shaded area in this case. And we need to divide this shaded area into 3 parts, I guess. Let's call this part as A1 from here to here. Let's call the area of this rectangle as A2, and let's call this part as A3. So I want to find the sum of A1, A2, A3, right? This is the question. Okay, let's start. What is A1? A1 is, okay, so A1 is in fact the area of this rectangle. Okay, I am talking about this rectangle now. The area of this rectangle minus the area of this part, right? Or you can represent A1 directly by writing a definite integral, okay? It is the integral of this curve. Secant theta, tangent theta, d theta from where to where, you see, from here to here. This is your negative function, and I am integrating it from this point to this point. So this is our interval now for A1. And if you take this definite integral, you will directly find not the area but minus of it, because your function is negative here. The result of the integral will be negative. That's why to relate it to the area, you need to take the absolute sign of it. Okay, so since the integral is negative, I need to take the absolute sign. That's why I need to put another minus sign in front of it. So let's try to compute this definite integral. Now we should consider the antiderivative of this function. So tell me a function whose derivative is secant times tangent. Okay. So it is in fact secant theta, right? Derivative of secant theta is exactly secant times tangent. So there's this extra minus sign here from minus pi over 4 to 0. Okay, this is what A1 is. Now let's compute A2. A2 is simple. It is a perfect rectangle, right? This base times the height, right? Base is pi over 4 times the height of it. You see the height is square root 2. Now A3. A3 can be represented by a definite integral, but if I take the integral from 0 to pi over 2 over this interval, from 0 to pi over 4, this curve, secant theta, tangent theta, d theta. This definite integral gives us the area under this curve, right? Where y equals secant theta times tangent theta. Okay, this is the curve. So this definite integral gives us this green shaded part. But what I need is this part. I mean, the rectangle minus this green shaded part will give us A3. That's why this is not A3, be careful. This definite integral gives this green part. Then A3 is whole rectangle, base times height. Let's write it again. Base times height minus this part, okay? And similarly, the result of this definite integral is secant theta from 0 to pi over 4, okay? And maybe I should put here a recall, like we should remember that derivative of secant theta is secant theta times tangent theta. That's why the integral of secant times tangent is just secant theta. Okay, so now I can put the result here. We were searching for A1, A2, A3, the total area. So A1 is this quantity minus, okay, I already did it here, minus secant theta from minus pi over 4 to 0, and then plus this A2 and then A3 plus 5 times square root minus. Okay, this integral is evaluated as again secant theta, right? Secant theta from 0 to pi over 4. Okay, this part is what comes from A1, this part is A2, and this part is A3. So I will leave the result like this. I want you to evaluate secant function at 0 and at minus pi over 4 and pi over 4. Okay, so let's move on. This will be the last example in this lecture video. Find the total area between the region and x-axis. Okay, let's try to find that. First of all, I think we should draw it, right? And it will be, this curve will have some positive parts and will have some negative parts. So let's try to search for its graph. So what is y function? I can write it in a simpler form like this. Okay, so the roots of this function are x equals 0 and x equals minus 2. And we can construct a sign table for it because we just want to understand where this curve is positive, where this curve is negative. So before minus 2, if you pick up a number and insert to your function, you will see that your function will get negative values. It is 0 here, it is 0 here. In between, it will get positive values and negative values here. So I'm not drawing the detailed graph here, but just to understand where it is positive, where it is negative, I will draw a very general quick graph. Like let's say this is -2, this is 0, and here is our curve. Our curve, I think, behaves like this. Between -2 and 0, it is a positive curve. Before -2, it gets negative values, and after 0, it gets negative values again. And what we want to do is, I want to integrate. I want to find the area between the curve and the region. Okay, over this interval from -3 to 2. Let's say this point is 2, so I want to find the total area, this part, and this part, right? Okay, so let's name them. Let's say that this is A1 and this is A2, this is A3. Let's start with A1. A1 can be represented in terms of a definite integral, of course, from -3 to -2 of our function. You see, this is our function, minus x squared minus 2x dx. But remember, your function is negative here. That's why the area is, in fact, the minus of your definite integral, right? Or you can just say that the absolute sign of it, okay? Because we know that the result of this definite integral will be negative. Area cannot be negative. That's why I need to take the absolute sign of it by putting an extra minus sign in front of it. Okay, so let's move on. I think I will write the total area. This is what A1 is, plus, what about A2? There is no problem about A2. It is directly this definite integral of your function. Because since your function is positive here, positive function, here it was negative function, and here again, negative function. And from -2 to 0, since it is a positive function, it will give us directly the value of A2, okay? The integral is itself positive, A2 and the integral are the same thing, but over 0 to 2, the definite integral of your function is again something negative because your function is negative there. That's why the result of the integral is negative. So you need to put an absolute sign to represent A3, which is the area, which is supposed to be a positive quantity. Okay, so now we can do all the computations. Okay, now I will just compute the integrals. The integral of x squared is at 1 to the power divided by the same power. Similarly, at 1 to the power divided by the same power, this expression will be evaluated from -3 to -2, plus, similarly, minus x cubed over 3 minus 2 times x squared over 2, this expression from here to here, and then inside absolute sign, x cubed over 3 minus 2 times x squared over 2. This expression evaluated at these upper lower bounds, but in the absolute sign. So the result will be, okay, you can easily insert -2 first and the -3, take the difference of the quantities, right? So let me just write one more line and then I can stop. If you insert -2, this part will get -8 over 3 minus, okay, these are gone. -2 for -4. This is then minus, now you will insert -3, okay? This is where I inserted -2, now I will insert -3. It is 27 over 3 minus 9, I guess. Absolute sign of this, plus insert 0, nothing comes from there. These are all gone, yes. Then insert -2. -2 we are inserting. It is 8 over 3 minus 4, okay, plus insert 2 minus 8 over 3, insert 0, 0, absolute sign. Okay, if you do all these computations, the result will turn up as this number. And this is how you compute the total area between your curve y equals f of x and x-axis. You should be careful about where your function is negative, where your function is positive. If your function is negative, for example, as it is here, between -3 and -2, the result of the integral will be negative. That's why to represent area in terms of this definite integral, which is negative, you have to take an extra absolute sign, okay? Similarly for A3, A3 is not directly the definite integral, but the absolute sign of it, as the integral will be negative there. But between -2 and 0, since your function is positive, integral will be positive, so it will be as the same as A2. No need to put an extra absolute sign here. So I stop here. Thank you for your attention.